Hello, today we're going to do section 1.3. Vector equations. So in this section, we're going to connect equations involving something called vectors to systems of linear equations, which we saw how to solve using augmented matrices and row reduction. Right? We're going to connect this idea to ideas of vector equations. Okay, so first, let's start with a definition for a vector. Okay, so a vector is a quantity, a mathematical quantity, with direction and magnitude. Okay, so if we think about it geometrically, a vector has a certain direction, and the magnitude is the length. The length is the magnitude. Okay, and the direction, we know, well, we use this arrow to point at the direction, but you could represent the direction as an angle as well. We'll see that later on. Okay, so let's start in 2 dimensions. In 2 dimensions, so this could be, for example, x and y, or it could be x1, x2. The important thing is that this is in 2 dimensions, and in mathematics we represent the real line from 0, 1, 2 to infinity, and everything in between as well. We represent this using the symbol r. When we have 2 real lines pointing in different directions, we call this r2, and this is a plane. We call this the xy plane, and this is the real line. And we can take it one step further, and we could have 3 variables, x, y, z, and we call this R3. Okay, and this is 3D space. And we saw that in the last section, linear equations like x plus 2y minus 3z equals 5. This is a plane in 3D. And it may look something like, like this. Right. This isn't actually this plane, but my point is that equations like this represent planes in 3-dimensional space. And when we have multiple, we have more linear equations like x minus 2y plus 3z equals, I don't know, let's say 10, then this would be another plane in 3 dimensions. And if they have an intersection, if they were to have an intersection, then these would have a solution. If they were parallel planes and they did not intersect, for example, this one and this one, then they would have no solution. We saw that. That's a review of the previous lectures. But I just wanted to mention that before we move on. Okay, so vectors in R2, we can represent them this way. This is the vector u and the vector v, and this means in R2. And let's say we represent vectors u and v with the following notation. Let's say 1, 2, and 3, 1. So the vector u vectors are represented using, in this case, x and y, using this notation, where this is a matrix with one column, okay, and 2 rows. And since we represent a vector as what we call a column matrix, because it has only one column, the x and y refer to coordinates in the plane R2. So for example, I'll have u equals 1, 2. It goes 1 in the x direction and 2 in the y direction. So here is u. And then v is 3 in the x direction and 1 in the y direction. And v we represent using this vector right here. Okay. I can say that two vectors are equal for example, if u, which equals u1, u2, is equal to v, which equals v1, v2, then u1 equals v1 and u2 equals v2. So since a vector is a mathematical quantity, then it shouldn't be a surprise that we can add two vectors. So for example, u plus v would be the column vector u1 plus v1, u2 plus v2. So in this case, u plus v would be equal to 1 plus 3, 2 plus 1, which would be 4, 3. Okay, so let's graph that. So I would have 4, 1, 2, 3, 3. So this is u plus v would be right here. And since by definition, a vector has just direction and quantity, that means if I have this vector here, okay, if I move this vector, I bring it up here, let's say. Let's say I bring it up here. And I did not change the length, and I have not changed the direction, then these two vectors are the same vector. Okay? So essentially I can take a vector and I can move it here, but as long as I did not change the direction and I did not change the length, then they are the same vector. Okay? So what I can do here is I can move this blue vector up here, v, and I can move this red vector u up here, and we see that vector addition, okay, so watch this, vector addition u plus v gives me what we call the resultant here. Okay? So essentially vector addition has the following geometric interpretation. If I take the vector u and I take the vector v and I place them from here is the beginning point, here's the end point, here's the beginning point, here's the end point, then the resultant is the resultant has the same starting point as u, and it has the same end point here as u plus v. So we have, this is the resultant r, which equals u plus v. And then vector subtraction would look something like this. So I would have, this is u, and this is v minus u, and this would be u plus v minus u. These would cancel, so I would just be left with v here. Okay. So what's the difference between these two? I'll let you figure that out yourself. Okay. Okay, let's look at R2. Since now we know what a vector is, well, any point in R2 can be represented with a vector. So if I have this point, I can represent it with this vector. If I have this point, I can represent it with this vector. Okay? And a vector here is called the position vector if it starts at 0, 0. Now, why do we call this the position vector? Because I can choose to move this vector, let's say over here, and it's the same vector mathematically because I did not change the length or the direction. However, this is not the position vector because it doesn't start at 0, 0. So by definition, we call the position vector the vector that starts at 0, 0. Okay? And that will help. I mean, it's good to put a name to it because sometimes we'll refer to it when we're doing specific mathematics. Okay. So if I have two vectors, or I'm sorry, if I have u, and I multiply u by, let's say, 2, then I'm just increasing the length of u by 2. And if I have negative 1 over 2u, I'm just decreasing the length by 1/2, and because it's negative, now it points in the negative direction, the opposite direction. Okay. I can take this further into 3 dimensions, and let's say I have 1, 2, 3 as a vector in 3 dimensions. Then in the x direction I go 1, in the y direction I go 1, 2, and in the z direction I go 1, 2, 3. So this would be my vector. U equals 1, 2, 3. Okay. And every point in R3, there's a vector associated with that point. We can take this further into R4 or Rn and say for R4 u would equal u1, u2, u3, u4. So we can even define vectors in 4 dimensions and define what it means to add vectors in 4 dimensions as well. Geometrically, it's a little more difficult to interpretate that, and it's above the scope of this course. There's also the 0 vector, which in 2 dimensions is just 0, 0. In 3 dimensions, it's 0, 0, 0, and so on. Now, in section 1.3, I want you to read the algebraic properties of Rn. Okay? Section 1.3. Read this part. It gives you 8 different properties for vectors. For example, u plus v is equal to v plus u. But that's pretty much obvious. Another one is that, c plus d times u equals this distributes. So there's scalar multiplication. We call this scalar multiplication, where so a vector is a vector, and what is not a vector, a number, is called a scalar. So 3, we call this scalar. For 3, we call this a vector. Okay? And we can multiply a vector by a scalar, so we can say 3 times 4, 1, let's say 4, 2, this would be equal to 12, 6. You just multiply both of them. Okay? We haven't defined what it means to multiply vectors yet. Okay, so don't worry about that yet. But we can multiply a number by a vector. Okay? So if we have 2 numbers c and d and we multiply by a vector u, or if we take the sum of c and d, we multiply it by u, we can distribute this and say it equals c times u plus d times v. I'm sorry, u. Okay. So you should read the algebraic properties of Rn in section 1.3. So I'm going to stop there in this video, and I'll upload another video tomorrow finishing up section 1.3. But you should read yourself, you should read everything up until when you get to the definition of linear combination. When you get to the word linear combination, stop. Because in the next video I will go over this. But what you should do is you should read everything in section 1.3 up until and also including algebraic properties of Rn.